Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good day to whom is my concern. So this is a lecture on chapter 4, the second law of thermodynamics. For this chapter, we divided it into two parts. The first part is about the concept of the second law of thermodynamics, and the second part is about the actual application of the second law of thermodynamics. This video is actually the second part of this chapter, which will cover about the application of the second law of thermodynamics in solving thermodynamic problem. Recall that in the video of the chapter 4 part 1, we have discussed about the thermal energy reservoir, which included the heat engine and refrigerator and heat pump system. Also, we have learned about the energy conversion efficiency, which are thermal efficiency and coefficient of performance for the heat engine and refrigerator and heat pump system respectively. Furthermore, we have discovered about the reversible and irreversible thermodynamic processes which lead to the ideal system that we call it as the Carnot cycle. Based on that, we have learned about the Carnot heat engine as well as the refrigerator and heat pump system. In this video, we will start by learning about the isentropic processes that based on the entropy principle. After that, we will apply all the knowledge of this chapter to define the isentropic efficiency of some steady flow devices such as turbine, compressor, pump, and nozzle. This chapter will be completed when we finish discuss about the concept of the exergy. As a reminder, in order to proceed this video, I do hope that you all have understand properly the first part of this chapter. Furthermore, you also need to cover the first, second, and the third chapters. Okay, let us proceed with the first topic in this part, which is entropy. As I point out in the video of the chapter 4 part 1, the second law states that the thermodynamic process must occur in a certain direction, not in any direction. Based on that, the thermodynamic expert have defined that the property that is called the entropy. Recall that the entropy is a quantitative measure of the molecular disorder of the substance for a system. Entropy can also be explained as a measure of the unavailability of heat to perform work in a thermodynamic cycle. That is because the heat need to achieve its equilibrium temperature before it can perform the work. Also, the second law predicts that not all heat provided to a cycle can be transformed into an equal amount of work. Some heat rejection must take place as well as maintain the equilibrium temperature. Mathematically, the entropy is defined as del Q over T in the condition of internally reversible system. So that for a reversible adiabatic process, the change of entropy from the final to the initial is equal to the integration of del Q net over T in the condition of internally reversible process. So for the reversible process, and at the adiabatic process, the change of entropy basically zero. This is due to the system can be reversed. Or we can say that in adiabatic system, since the change of entropy is equal to 0, then the final entropy must equal to the initial entropy. So that's why the reversible adiabatic process is also called the isentropic process. The entropy change and isentropic relationship for a process can be summarized as follow. Okay, the first one is for the pure substance. In the case for the pure substance, we can write it as delta S, or the change of entropy is equal to S2 minus S1, and this answer basically is equal to 0. So therefore, we can write it as isentropic process is equal to final entropy is equal to initial entropy. Please bear in mind that the unit for the entropy that is written in a small letter, or we call it the specific entropy, is kilojoule per kilogram Kelvin. Okay, number 2. If the system deal with the incompressible substance such as liquid and solid phase. Okay. Alright. So S2 minus S1 is equal to specific energy at average multiplied by the ratio of the temperature. Sorry, the unit here is kilogram of kilojoule per kilogram Kelvin. Okay, because the unit of specific heat also kilojoule per kilogram Kelvin. Therefore, we can also write as for the incompressible substance, the temperature at the final state is equal to the temperature at the initial state. Okay, number 3. Okay, the third case is for the ideal gases. Okay, for the ideal gases, as I point out in chapter 2, that is for this course, we will only use the approximation method for the case of ideal gas, where we only use constant specific heat, normally at room temperature of 27 degrees Celsius or 300 Kelvin. So therefore, the entropy change for the OR process is equal to S2 minus S1, specific heat at constant volume in the case of average. So the average here is, please remember, 300 Kelvin, ln T2 minus divided by T1 plus R, the gas constant, ln V2 minus V1. Also, it can be calculated by using the specific heat at the constant pressure, where at the end of the day, so you get Cp average ln T2 over T1 minus R ln P2 over P1. So if you get this part, so for the, if you use the average specific heat at the constant volume, you have to use the plus for the volume, and for the pressure, this is the minus. So based on that one, okay, in the case of isentropic process, so this is the case for isentropic process, we use the relationship of the isentropic process that we have been discussed in chapter 2 for the boundary work for an adiabatic process. So as a T1 over T2, okay, is equal to P1 over P2 power of K minus 1 over K is also equal to V2 divided by V1 power K minus 1. Okay, for your early information, P1 over P2, we call it pressure ratio, and V2 over V1, we call it volume ratio, or we call it compression ratio. So from this equation, basically we can do it one by one. So because this equation Okay, in this equation, basically we relate three components, which is temperature, pressure, and volume. So if you do it one by one, we can get T2 over T1 is equal to V1 over V2 power of K. If you compare this equation to the previous equation, so this is written T2, and then this one is written T1. So basically this is the ratio. You can swap the denominator and nominator as long as they are consistent. So if you see this one T2 and this one T1, so this one is basically V2. Now the equation become V1. So similarly, so this is the power of K minus 1. This also power K minus of 1. So this is the relationship between the temperature and the volume. Okay, so as I tell you earlier, the V1 over V2, we call it as the compression ratio. So the next one is basically the relationship between temperature and pressure. Similarly, we can get from this equation. Okay, so T2 minus T1 is equal to, sorry, T2 divided by T1, okay, at isentropic process is equal to P2 over P1 in the power of K minus 1 over K. So finally, we can do the relationship between the pressure and the volume, okay. Alright, P2 over P1 is equal to V1 over V2 power of K. Alright, so this is what we call the three relationship based on what we call the general equation for the isentropic process. Note that K is basically the specific heat ratio, which is it is calculated as Cp over Cv. Alright, so this is the sample problem 4.9. So basically this sample problem is to demonstrate how we are going to use the knowledge of the entropy chain and isentropic process in order to solve a thermodynamic problem. Okay, now let us read the question. So the question said that steam, okay, please do remember when we talk about steam, the substance is basically water. Please do remember that in our study, we only have three types of substance. The first one is water. The second one is refrigerant R134A. And the third one is ideal gas. Okay, given a pressure of 1 megapascal, 600 degrees Celsius. So 1 megapascal is equal to 1000 kilopascal. Expand in a turbine to a 0.1 megapascal. If the process is isentropic, please do remember the process of isentropic means S2 is equal to S1. Okay, then the question asks us to find the temperature and then the final enthalpy and finally the turbine work. Okay, based on this one, so we know that this is what we call the turbine. Turbine is under the category of the engineering flow devices, which is it is under the open system. So when it's open system, in our case, the volume doesn't change. So what we have to do is we have to do the mass balance. So in this case, mass that entering to the system is equal to the mass that leaving to the system. So from this one, we can define our energy balance equation. So the energy balance equation is energy that enters into the system must equal to the energy that leave the system. So when we do complete what we call analysis for the turbine, as I explained in the chapter 3, we can get m dot 1 multiplied by h1 is equal to m dot 2 multiplied by h2 plus work out. Please do remember. So for the turbine, we have work out, we don't have work input. So the heat all is neglected. Potential and kinetic energy also be neglected. So when we rearrange this equation to get the work out, what we get is m dot is equal to h1 minus h2. So basically, this is our main equation in order to determine the work output to answer the question number 3. Okay, alright, so from this one, we have to determine its required properties. So the required properties, so this is steam, so we have to refer to the table. Okay, so we go state by state. At state number 1, we have the pressure 1 megapascal. We have T1 is equal to 600 degrees Celsius. So based on this one, we can check it phase. So it will fall under the category, also under the superheated. So from superheated, we can refer to the table A6. We can read at the 1 megapascal table at the 600 degrees Celsius. We can get H1 is equal to 3698.6 kilojoule per kilogram. Similarly, at that point, we can determine, we can take the data of the entropy at state number 1 is equal to 8.0311 kilojoule per kilogram Kelvin. So now we have completed state number 1. So we go for state number 2. Please do remember that the process is isentropic. Therefore, S2 is equal to S1. So in state number 2, okay, we have the pressure of 0.1 megapascal only. Okay, but we don't have any other properties. So please do remember that in order to define the properties, we have at least minimum 2 intensive properties. So in this case, we can use the pressure 0.01 megapascal and second entropy or entropy at state number 2 is equal to 8.0311. This is actually equal to the entropy at state number 1, since isentropic process is equal to S2 is equal to S1. So from this one, we can check the phase. When you check the phase, you will get it at a saturated mixture. Please refer to the chapter 2 in order to determine the phase. Please do remember we have 5 possible phase. The first one is the first one is compressed liquid, saturated liquid water, saturated liquid, mixture, saturated vapor, and finally we have superheated. So from that one, we need to calculate if it fall under the what we call the saturated mixture, then we have to determine the quality of the mixture. So we found that the quality of the mixture is equal to 0.984. So based on that one, we can determine what we call the final entropy as HF plus X HFG. So we put all the data. HF is equal to 191.8 based on the table, plus X is equal to 0.984 multiplied by HFG is equal to 2392.1. Based on that one, we can calculate, we can get it as well, 2545.6. Okay, since the state number 2 is fall under the saturated mixture, then temperature 2 must equal to the saturated temperature at the given pressure of the 0.01 megapascal, and from the table we found it is the value is equal to 45.81. So that we already answered the first question, which is the final temperature. Okay, and the final entropy also we already found. This is equal to H2 is equal to 2545.6. So this is answer for the final entropy. And finally, the work done, since we already have the equation, this is equal to work dot out is equal to H1 minus H2. So we can get it what we call 3698.6 minus 45.6. So you get the work output is equal to 1153 kilojoule per kilogram. So for this equation, you have this one is equal to m dot. So please do remember that work dot is equal to m, okay, dot multiply by work out. Okay, sorry, equal to work out, so that you can cancel this m dot as you cancel this m dot. Okay, so what you get is basically work out is equal to H1 minus H2. So that the final answer for the work output is equal to 1193 kilojoule per kilogram. Okay, this is sample problem 410. Also exemplify the thermodynamic problem that require the knowledge of the entropy or the isentropic processes. Okay, let us look at the question. It is said that 1 kilogram of R134A. So now we can identify our substance, which is the refrigerant R134A, initially at 600 kilopascal. So this is the pressure and 25 degrees Celsius. Undergo a process during which the entropy is kept constant. So the process that entropy is keep constant is basically isentropic process. What is mean by constant? S2 is equal to S1 until the pressure drop to 100 kilopascal. So the question asks us to determine the final temperature of the R134A and the final specific internal energy. Okay, so our substance is basically R134A. Process is isentropic, which is equal to S1 is equal to S2. Okay, the data given, the mass is 1 kilogram, pressure 600 kilopascal, T1 25 degrees Celsius, P2 is equal to 100 kilopascal. Okay, we go one by one. Okay, now we go to the state number 1. So in order to define the state, we need two intensive properties. So from the data that given to us, we do have the pressure as well as the temperature. Now the data required to define the state number 1 is complete. Okay, so P1 is 600 kilopascal, T1 is equal to 25 degrees Celsius. Based on our table, we found that T1 is bigger than or higher than T saturated exceed 100 degrees Celsius, which is the value is 21.55 degrees Celsius. Then state number 1 is in the superheated region. So based on that, from table A13, please do remember this is R134A, this is not water. So please check the table properly. So from the table A13 at 0.6 megapascal and 25 degrees Celsius, and we need to use the interpolation. Please master your mathematical method or mathematical knowledge for the interpolation. So T is equal to 20 degrees Celsius. S is 0.9383. 25 degrees Celsius. That is what we want to calculate. So at 30 degrees Celsius, we get 0.9703. So from this one, we can perform the interpolation. So we can get the value of S1 is equal to 0.9543 kilojoule per kilogram. So the question is, why we need to determine this S1? This is because we want to define the state number 2. Please do remember, all the question asks the final temperature and final specific energy. So basically, we want to define state number 2. However, based on the data given to us, we have not enough data. We only have the data of the pressure at state number 2. That's why we cannot define state number 2. So the only data that we can calculate is by using the entropy at state number 2, because S2 is equal to S1, since this process is the process which entropy is keep constant. So now we can define state number 2. So P2 is equal to 100 kilopascal. S2 is equal to S1. This is equal to 0.9543. So based on the table, we found that S2 is higher than Sg at 100 kilopascal. So which is our value of S1 is equal to 0.9543. The value of Sg is equal to 0.95183. So the second phase also still under equivalent to state 1, which is in the superheated region. So from this one, we can go from table A13, 0.1 megapascal and 25 degrees Celsius. From that one, we can interpolate to calculate the answer of T2 and U2. Okay, so that interpolation, you have to do it by yourself to test your understanding and to test your skill for the interpolation method or interpolation technique. Okay, please do it. Please complete this sample problem. Okay, this is a practice problem 4.2. So this practice problem is basically to provide you the tutorial regarding to the problem of the entropy and the isentropic process. Please complete all the question given here. So to test your understanding and to make sure you understand everything for this topic. Okay, similarly, these are other question for the practice problem 4.2. I do hope that you really completed this practice problem in order to test your understanding. By that, we have completed the first part or the first topic of this video, so which is the entropy principle and isentropic process. Okay, now we move on to the second topic in this video, which is the isentropic efficiencies of some steady flow devices. As we all aware of, the efficiency of the actual device or component or system is always lower than the ideal one. This is due to the irreversibility that include friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, electric resistance, inelastic deformation of solid, and chemical reaction, and thus that their effect is always downgrade the performance of devices. So we have discussed this irreversibility in the topic of the reversible and irreversible process. In engineering analysis, it would be very desirable to have some parameters that would enable us to quantify the degree of this degradation of energy in these devices. An ideal device would be generally adiabatic and have no irreversibilities. In an example, an isentropic device. The parameter then expresses how efficiently an actual device approximates to an idealized one is called the isentropic or adiabatic efficiency. The isentropic efficiency are defined differently from different devices since each device is set up to perform different tasks. In general, the isentropic efficiency is technically defined by comparing the actual performance of the devices to their performance under the isentropic condition for the same inlet and exit state. In another word, the performance of actual compared to the performance of ideal one. Okay, let us see the isentropic efficiency of some selected devices. In this slide, I will explain about the isentropic efficiency of the turbine. Based on chapter 3, we have learned about the turbine. It is a machine in which the kinetic energy of a moving fluid is converted into the mechanical energy by causing a blade or rotor to rotate. The pressure difference of a typical turbine operation can be illustrated in HS diagram here. So this is the HS diagram. So from this one, so this is the line of the pressure, the red in color. So as you can see here, the red in color, this is the line of the pressure. Similarly, this is also the line of the pressure. Obviously, the pressure 1 is higher than pressure 2. Okay, so what we have for the turbine, basically, so the turbine, the fluid will enter at the turbine at high pressure. After that, it will goes down to the exit of the turbine at a lower pressure. So for the turbine, the inlet pressure is basically higher than the exit pressure. Based on this one, we can write it as pressure 1 here, and this is pressure 2, and this is state number 1, where state number 1 is the inlet of the working fluid into our turbine, and this is, we have two state number 2. The first one is state 2s. State 2s is basically the exit state at the turbine under the condition of isentropic or the ideal process. As you can see here, so we have defined earlier that for under isentropic process, S1 is equal to S2. So that means S at state number 1 is equal to S at state number 2. So here we will return it S2S is equal to S1. However, in the actual condition, so the entropy always increase. So the actual state number 2 will fall in this area. So we can get that S2 here. So now we have the deficiency, or we have the different entropy from state 2A and state 1. Okay, so now if we draw the H diagram, so sorry, the H point, so this is the point of H2S or isentropic condition, and this is the H for actual state. From this one, this is the work of actual, this is the work of isentropic. So based on this one, you can see the the actual work is lower than the isentropic work. By definition, the isentropic work is the maximum possible work output that the adiabatic turbine can produce. Therefore, the actual work is less than the isentropic work. Since efficiency are defined in the topic of heat engine to be less than 1, then the turbine isentropic efficiency is defined as actual turbine work over isentropic turbine work, or WA divided by WS. So WA is calculated as H1 minus H2A, and isentropic turbine work, or WS, is defined as H1 minus H2S. So please do remember, this is smaller, this is bigger. Smaller divided by bigger, you never get more than 1. This is a sample problem 411. This sample problem is used to exemplify the isentropic efficiency of the turbine. Okay, so let us read the question. The first one, it said that steam. Okay, it already gives to us the working fluid. So working fluid, if it said steam, this is water. So it gives at 1 megapascal, 600 degrees Celsius. So this is one state. So expand in the turbine. So expand. So expand, that means number 2 is 0.01 megapascal. Then it said that the isentropic work. Okay, the question already given to us. The isentropic work of the turbine is equal to 1153 kilojoule per kilogram. If the isentropic efficiency of the turbine is 90%, it already gives to us 90%, then we have to calculate the actual work. Okay, so also the question asks us to find the actual turbine exit temperature. Exit is state number 2, or the quality of the steam. So basically, so we don't know what is the phase at the exit of the turbine. Either it is in the compressed liquid, mixture, or in the superheated. If it in the mixture, then we have to determine the quality. But if it in the what we call compressed liquid or in the superheated, we just calculate the exit temperature. We know that the temperature at the mixture is equal to saturation temperature. Okay, the first one. Okay, in order to solve what we call the actual work. Okay, so based on the equation of the turbine efficiency, okay, isentropic efficiency of the turbine is equal to work actual divided by isentropic work. Okay, it also equal to H1 minus H2A. Please do remember A mean actual divided by H1 minus H2S. S is equal to isentropic. Okay, so the question already give us what we call 1153 kilojoule per kilogram. This is basically WS. Okay, so by using this part of equation, okay, then we can rearrange. We can get WA is equal to isentropic efficiency of the turbine multiplied by WS, or isentropic work. So 90% of the isentropic efficiency, when we want to do the calculation, we can write it as 0.9 multiplied by 1153, and the answer is the work actual is equal to 1037.7. As you can see, this is a lower than the isentropic work. Okay, so next is the question asks us to determine about the actual turbine exit temperature. So if it is the actual turbine exit temperature, basically this is just what we call the properties of pure substance, similarly as we define at the chapter 2. Okay, so what we have to do is we need two intensive properties at the state number 2. If you look at this question, we only have one properties at state number 2, which is the pressure. Therefore, we could not define state number 2. So, however, so we can use the other way around, which is isentropic. So, we know that isentropic is equal to S2, mass equal to S1. So, we have to determine what is the value of S1 first before we can proceed to the final for the exit turbine. Okay, so now we go for state number 1. Okay, at state number 1, we already have the pressure 1 megapascal. We have what we call temperature 600 degrees Celsius. Okay, based on this one, we have to determine the phase. Either it is in the compressed liquid, saturated liquid, mixture, saturated vapor, or superheated. Okay, so based on my calculation, I found it state number 1 is in the superheated region. Okay, you have to do it by your own. So since it is in the superheated region, then I can simply check at what we call table A6 superheated. I can extract the data. H1 is equal to 3698.6 kilojoule per kilogram, and I can get S1 is equal to 8.0311. So now I have what we call S1. Okay, all right. So I go to state 2S. Okay, this is the exit of the turbine in the condition of isentropy. Okay, so P2 is equal to 0.01 megapascal, and we know that for isentropic, S2S is equal to S1 is equal to 8.0311. So we already have two intensive properties. From this one, we can check the phase. So based on my calculation, I found that the state is in the saturated mixture. So since it is in the saturated mixture, so I found that X2S is equal to 0.984 and H2S is equal to 2545.6. So what you have to do is you have to expand this answer. First, you have to determine what we call the phase of this state 2S. So whether the pressure, whether the entropy at 0.01 megapascal is lower or higher than the entropy at state number S2S, which is 8.0311. Okay, all right. So then if found it in the saturated mixture, so you can use what we call the equation for the quality. X is equal to SF minus S2 minus SF divided by SFG. Okay, then you can get H2. Similarly, H2S is equal to HF plus X HFG. Okay, all right. So now we have H2S. Okay, in order to determine the actual exit temperature, we can use what we call this equation, which is we know that work output in the actual condition is equal to H1 minus H2A. So we can rearrange this equation. We can get that H2A is equal to 2660.9 kilojoule per kilogram. So why we need this value? Because at state 2A, we only given the value of the pressure is equal to 0.01 megapascal. So we need another property. So now we have H2A. So H2A is equal to, by our calculation, we can get it is 2660.9 kilojoule per kilogram. So based on that one, we can go to the table A6 superheated at the column of 0.1 megapascal. So we have to find what is the value of 2660.9 for the enthalpy. From that one, we can get the temperature. So I think in this case, you have to do the interpolation in order to get the value of T2A is equal to 86.85 degrees Celsius. Okay, so please do it again, this sample problem, in order for you to understand how it works. Okay, the next devices that we should learn in this topic is the compressor and the pumps. Recall that the compressor is used to increase the pressure of the compressible fluid such as ideal gas, and the pump is used to increase the pressure but for the incompressible fluid such as compressed liquid or water. So the pressure difference of a typical compressor and pump operate can be illustrated in this HS diagram. So this is HS diagram. Similarly, in HS diagram, we have the line of the pressure. Okay, now, sorry. So for the pump and compressor, so for the compressor, basically the inlet of the compressor is in a lower pressure, but the outlet of the pressure at the outlet is higher than the pressure at the inlet. So P1 is lower than P2. Okay, so now let's say this is state number 1. If it isentropic, so S1 is equal to S2S. Okay, however, okay, for actual condition, we know that for actual condition, the entropy must always increase. Therefore, the state number 2 is fall here. So the same line pressure as state of isentropic. So based on this one, we found that the work isentropic required by pump or compressor is lower than the work that of pump or compressor require in the actual condition. In the case of the compressor and pump, the isentropic work is the minimum possible work that the adiabatic compressor requires. Therefore, the actual required work is much greater than the isentropic work. Similarly, since efficiency are defined to be less than 1, as we learned in the topic of heat engine, then the compressor isentropic efficiency is defined as isentropic compressor divided by actual compressor work. So this is because work isentropic is basically lower than the actual work of the compressor or the pump. In the case of the pump, okay, so this is isentropic efficiency of the compressor. So when the kinetic and potential energy are negligible, we can say that isentropic efficiency of the compressor is equal to H2S minus H1 divided by H2A minus H1. Okay, in the case of the pump, the isentropic work required is also can be calculated as, so for work pump, isentropic work also can be calculated as specific volume multiplied by the pressure at exit of the pump minus the pressure at the inlet of the pump, or we can say that this is equal to delta P. Okay, so divided by H2A minus H1. Please remember that this equation, so basically, let me clear this one. Okay, basically, this equation, which is V multiplied by P2 minus P1 is equal to H2S minus H1. So this equation is equal to equal. Okay. So, however, I have explained it in the chapter 3, so that please recall the derivation of the pump in the chapter 3 to understand how this formula is obtained. Okay, now let us see the example of the isentropic efficiency of the compressor in the sample in this sample problem for 12. Okay, all right. It said that air. Okay, so now our substance is air, ideal gas. So please remember, if we talk about ideal gas, we have to use what we call our ideal gas law, which is PV is equal to M R T. Okay, all right. Air enters a compressor and it is compressed adiabatically. So adiabatically, no heat loss, from 0.1 megapascal, 27 degrees Celsius. Okay, please check the unit. So this is 27 degrees Celsius. The substance is basically air. So you have to convert it by plus 273 to a final state of 0.5 megapascal. And then the question said, find the work done on the air for the compressor isentropic efficiency of 80%. Okay, all right. So the efficiency of this compressor is 80%. So we have to determine the compressor work done. Okay, assume constant specific heat of air at the room temperature. So it said that just a work done. So when it already said the work done, so please do remember this is basically referring to the actual. Okay, so that means the question asks us to determine the actual work done for the compressor. Okay, similarly, we start from the energy balance equation. So this is the energy balance equation for the compressor that we have derived in chapter 3. So please do not memorize this equation, you should start it from the energy balance equation. Energy in minus energy out is equal to the change of energy of the system. So this is open system, so the change of energy system is equal to 0. So energy in is equal to energy out. So for the compressor, it said that adiabatic, no heat loss. And compressor, we don't have any work output, we only have the work input. Similarly, we can neglect the kinetics and potential energy. That's why we can get what we call our equation. Isentropic compressor of isentropic work for the compressor is equal to m dot multiplied by H2S minus H1. So work compressor is equal to W dot compressor at isentropic divided by m dot. So we can get that H2S minus H1 as I explained earlier. So we know that for ideal gas, H is equal to CPT. Then we can convert our work, isentropic work for the compressor is equal to Cp T2S minus T1. So this is what I said. We use the approximation method where dCp we take at 300 Kelvin. So if you refer to the table, okay, you can get Cp, okay, at 300 Kelvin is equal to 1.005 kilojoule per kilogram Kelvin. Okay, this is the value of Cp. Please refer to the book. Okay, also we know that the isentropic process for ideal gas law. So as I mentioned earlier, it is T2S divided by T1 is equal to P2 over P1. Similarly, if you look at what we call the table, the specific heat ratio is equal to 1.4. This value is not given in the question, but you have to refer it in the table. So from this one, you can rearrange. What you get is T2S is equal to 27 plus 273 multiplied by 0.5 divided by 0.1 power of 0.4. Yes, this is question. K minus 1, 1.4 minus 1 is equal to 0.4 divided by 1.4. So now you can get T2S is equal to 475.4 Kelvin. Okay, so therefore we can get what we call work isentropic. So work isentropic is equal to 1.005. As I mentioned earlier, this is the value of the Cp. Okay, so 475.4. So this is we calculated here. Minus 300. 300 is basically, where is 300? 27 degrees Celsius. Okay, so you can get the value of isentropic work, 176 kilojoule per kilogram. Okay, so we know that isentropic efficiency is equal to work isentropic divided by work actual. So then you can rearrange work actual is equal to work isentropic divided by the efficiency. So you put the value, work isentropic is 176, isentropic efficiency is equal to 80% or 0.8. Finally, you can get actual work for the compressor is 220. If you can see here, the actual work is basically higher than the isentropic work output. So this is how we are using what we call the knowledge of isentropic efficiency of the compressor to determine what we call the problem or to solve the problem of the compressor. Okay, this is sample problem 413. Obviously, it is the example for the isentropic efficiency of the pump. Okay, the question said that a pump, okay, is used to draw refrigerant R134A. Okay, this is the refrigerant R134A. Okay, at negative 30 degrees Celsius and 100 kilopascal to 360 degrees Celsius. So basically, if you see the thermodynamic problem, either in the test, either in the assignment, either in the final exam, so normally we give what we call the data. One is complete data, okay, two intensive properties and the other one is only single. So you have to find another properties in order to define the state. So we know this is pump. So pump must work under the condition of the compressible. So that's mean this refrigerant must be in the compressed liquid. Okay, so the question said if the efficiency of the pump is 85%, okay, it asks us to determine the isentropic specific work of the pump. Second one, actual specific work of the pump. The third one, specific enthalpy R134A after the pump. Okay, so this is okay, we go one by one. Okay, we know that the efficiency of the pump is equal to work isentropic of the pump divided by actual work of the pump. So for the pump, we know that it is equal to V multiplied by P2 minus P1, and work actual is equal to H2A minus H1. Okay, all right, so since this is a pumping what we call incompressible, so then state 1 always assumed to be saturated liquid. So V1 is actually about VF at negative 30 degrees Celsius. Please refer to the chapter 2 why we take negative 30 degrees Celsius instead of 100 kilopascal. Okay, so the value is 0.000723 meter cube per kilogram, and similarly H1 is about approximately HF also at negative 30 degrees Celsius. So this is 12.65 kilojoule per kilogram. Okay, so the first one, isentropic specific work of the pump. Ws is equal to specific volume multiplied by P2 minus P1. This is equal to 0.1873. Okay, B, the actual specific work of the pump. So from the equation of what we call efficiency, okay, sorry, we can rearrange this equation. Work actual is equal to work isentropic divided by efficiency of the pump. We can get it as 0.2204 kilojoule per kilogram. And finally, we have the specific enthalpy of the R134A. So based on this equation, so this equation, as I mentioned earlier, okay, V is equal to P2 minus P1 is equal to Ws. This is also equal to, okay, H2A minus H1. Okay, so we rearrange this equation. We can get H2A is equal to work actual plus H1. So we can get it as 12.8704. So this is how we are going to use what we call the isentropic efficiency equation of the pump to solve the problem of the pump. This is the final devices that we should be learned in this course under the topic of isentropic efficiency, which is the nozzle. Please refer to chapter 3 for the definition and the function of the nozzle. The pressure difference for a typical nozzle can be illustrated in this HS diagram. So please remember that in the HS diagram, we have the pressure here. Okay, and please note that this line of the pressure, this is the constant pressure line. So this is the constant pressure line. Okay, all right, so by definition, the nozzle is a device that being used to increase the value of the velocity in the substance, okay, by reducing the pressure of the substance. Therefore, the inlet pressure of any nozzle must always higher than the in-exit pressure. So if we take this one as a state number 1, or this is the state at the inlet of the substance to the nozzle, then we can get this is the exit isentropic state for the nozzle, where we know that in isentropic condition, S2S must equal to S1. Okay, for the state, for the actual state, we have to understand that. So actual state S2 must always higher than S1. So then the actual state is fall in this pressure. Please do remember that pressure at state 2S is equal to the pressure at state 2A, because this is the line of the constant pressure. From this one, we can calculate what we call the magnitude of work. Okay, so this is H1 to H2A. So this is the actual work required by the nozzle, and this one the isentropic work that being produced by the nozzle. Okay, all right. So based on that one, we can determine the nozzle efficiency as H1 minus H2A divided by H1 minus H2S. Okay, based on the energy balance equation for a steady flow, for the nozzle, we have no work. We can neglect the potential energy. Therefore, the conservation of energy principle for the nozzle can be written as H1 plus velocity 1 power of 2 divided by 2000. Please recognize this equation. So basically, this is the kinetics energy at the inlet. So must equal to the enthalpy at the exit of the nozzle plus the kinetics energy at the exit of the nozzle. Okay, so we can rearrange this equation. So basically this equation we can rearrange for the ideal and actual condition. Okay, the first one, let us see for the ideal. In the ideal condition, we can rearrange that H1 minus H2S is equal to velocity 2s power of 2 divided by 2000 minus velocity 1 power of 2 divided by 2000. In the case of the actual condition, so we can change the value of the exit enthalpy from the isentropic to the H2A. Similarly, for this velocity in the isentropic condition, we can change it to the ideal condition. So the equation for the energy balance equation for the nozzle is basically H1, this is velocity 1, H2 velocity 2. When we rearrange, we can get it as H1, H2. But for the velocity, it is velocity 2 minus velocity 1. So that the finally we can rearrange this equation, okay, for the nozzle efficiency as H21 minus H2A divided by H1 minus H2S. Please do remember that H1 minus H2A, this is the equation of the work for the actual work divided by isentropic work of the nozzle. So we have defined earlier that H1 minus H2A is this one. So this is actually the velocity 2A power of 2 minus velocity 1 power of 2. Similarly, so H1 minus H2S, we have defined here as velocity 2s power of 2 minus velocity 1 power of 2. Okay, however, for the nozzle, normally, okay, the inlet velocity is too small and always be neglected. So the inlet velocity. So in this equation, we can cancel out the inlet velocity. So in general, the nozzle efficiency will become as nozzle efficiency H1 minus H2A divided by H1 minus H2S is equal to velocity at the exit in the actual condition divided by velocity at the exit in the isentropic or ideal condition. So we can say that for the nozzle, the efficiency is depend only for the velocity of the fluid. Okay. This is sample problem for 14. This is an example of the isentropic efficiency of the nozzle. Okay, let us read the question first. Okay, the question said that air. Okay, our substance is air. So please do remember, air is ideal gas. So we have to use the equation of PV is equal to mRT. Initially, it has 200 kilopascal and 950 Kelvin. Enter an adiabatic nozzle at low velocity. This is low velocity, and it is discharged at the pressure of 110 kilopascal. If the isentropic efficiency of the nozzle is 92%, determine the maximum possible exit velocity, B, the exit temperature, and C, the actual exit velocity of the air. So basically, the equation A is equal to equation B. Question A is equal to question C. The difference is this is the maximum possible exit velocity and this is the actual. What does the maximum possible exit velocity mean? So we know that for any device, the maximum always at the isentropic or at the ideal condition. So this question is actually asking you what is the isentropic velocity of the nozzle. Okay, so but you have to understand, okay, this is what we call understanding of the question. Maximum must always in the isentropic condition. Okay, so the question also said that assume constant specific heat of air at room temperature. Okay, so when we assume constant specific heat, basically this is we reflects our calculation. So we have to take what we call the specific value of the air at the constant room temperature, which is 300 degree Kelvin. The value for air, Cp is equal to 1.005, Cv is equal to 0.718 kilojoule per kilogram Kelvin, and the specific heat ratio K is equal to 1.4. So that is the value. Okay, in order to solve this one, we can see one by one. Okay, first one, the maximum possible exit velocity. Okay, this is we can calculate it from the isentropic process of an ideal gas that we have learned earlier. So basically we know that T2S, okay, over T1 is equal to P2S. So basically P2, there is no S. Okay, because P is a constant pressure. Okay, so P2 divided by P1 is equal power of K minus 1 over K. So we can rearrange this equation. So we can get the value of T2S as T1 multiplied by P2 over P1, K minus 1 over K. So put the value, T1 is equal to 950 Kelvin. Okay, this is kPa, can be cancelled out. Okay, and you can get the value of the T2S as 800.83 Kelvin. Okay, so in order to determine the possible exit velocity, we have derived the equation from the energy balance equation for the nozzle. So energy in minus is equal to energy out. So actually it starts from energy in minus energy out is equal to the change of energy of the system. Since this is an open system, so the change of energy of the system is equal to 0. Therefore, we can get energy in is equal to energy out. So for the typical nozzle, H1 plus velocity 1 power of 2 divided by 2 or 2000. So this is just a unit, yeah, 2000. So it's equal to H2S plus velocity 2 S power of 2. Okay. Alright, divided by 2. Okay, so now they said that isentropic process. So isentropic process, that's why we use the value of this one. Okay, velocity 2s. Okay, so since the inlet velocity is very low, then we can assume that velocity 1 is equal to 0. So we can cancel out this one. So based on this one, we can arrange this equation. So this equation we can rearrange by taking this velocity at the front. Okay. Alright. So we can get this is equal to power of 2. 2 multiplied by H1 minus H2S. Okay, so we know that for ideal gas, H is equal to CPT. Then we can get 2 CPT1 T2S. We already calculate T2S as 800.83. So substitute the value in this equation. So we can get the velocity 2 is equal to 547.57. So this is the maximum possible velocity, where please do remember this is isentropic. Okay, alright, so the isentropic. Okay, so this is the maximum. So the actual must be less than this one. Okay, please do remember. Okay, B. So they ask about the exit temperature. So the exit temperature, we can use what we call the nozzle efficiency. H1 minus H2A divided by H1 minus H2S. So this is, we know that H is equal to CPT. So CPT1, CPT2A divided by CPT1 minus CPT2S. Cancel out CP, 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 CP. So we can get T1 minus T2A over T1 minus T2S. So then we can get T2A is equal to 812.76. Okay, so this is the answer for B. Okay, the exit temperature. So, this is the actual exit temperature. Okay, next is the actual exit velocity. So basically, this is, as I said earlier, this is similar to here. Okay, A. So therefore, you can use this equation. Basically, you can use this equation. So this is the same equation basically. Okay, so except the value of the T2S, replace it with the T2A. Okay, that's all. Okay, substitute the value of T2A into this equation, then you should get what we call the actual velocity of the air. Okay, please do it yourself. Please complete this sample problem. Okay, to test your understanding. All right. Okay, this is the practice problem 4.3. This practice problem is used to test your understanding regarding to the knowledge of the isentropic efficiency of the steady flow devices, starting from the turbine, compressor, and nozzle. Okay, please complete the entire question in this practice problem. Actually, as a student, you need to complete the entire practice problem by yourself, not copy from other, in order to excel in this subject. In this slide, I will talk about the concept of exergy, which is the last part of the chapter. Okay, technically, exergy is defined as the useful work potential of a given amount of energy at some specified state, which is also called the availability or available energy. In another word, the exergy is opposite than entropy. Exergy is basically the energy that is used to convert to the useful work, but entropy is the energy that could not be converted into the useful work. During any thermodynamic process, whether it is isochoric, isobaric, isothermal, adiabatic, or polytropic processes, the energy is never destroyed. It only changes from one form to another form as explained by the first law of thermodynamics. However, in contrast, exergy is account for the irreversibility of a process due to the increase in entropy. Therefore, the exergy is always destroyed when a process involves a temperature change. In addition, a system is said to be in the dead state when it is in thermodynamic equilibrium with the environment. That means the temperature of the thermodynamic system is equal to the temperature of the surrounding. Since second law said that the energy will naturally transfer from higher degree of energy to a lower degree of energy, then no energy will be transferred if the system and surrounding have equivalent temperature. Therefore, it is called the dead state. A system delivers the maximum possible work as it undergoes a reversible process from the specified initial state to the state of its environment, which is the dead state. This represents the useful work potential of the system at the specified state, and that is called the exergy. Exergy represents the upper limit on the amount of work for a device that can deliver without violating any thermodynamic laws. Thus, this is a glimpse of the concept of exergy. If you can see in this figure, basically, if we have a total energy, okay, part of it is unavailable energy, or in this case we call it as entropy, and the other part is we call it exergy, which is the amount of energy that being converted into the useful work. So basically this is what we call the concept of exergy. By that, we have concluded this chapter, which is the second law of thermodynamics. So with that, thank you very much, and please stay safe wherever you are. So see you in the next video. Wassalam.